Welcome everyone to the first workshop in the Introduction to Data Science workshop series. So my name is Dr. David Pugh. I am a staff scientist at the King Abdullah University of Science and Technology's Visualization Core Laboratory. I'm also a certified instructor with software and data carpentry. So today in this workshop, we're going to talk about the shell, an introduction to the bash shell. So, and if you're watching this video on YouTube, sometime in the future after I'm done recording it, then all of the important links for today are going to be listed underneath the video in the kind of additional details about the video. So all the links and things that I reference in here are going to be available down below the video, and the video will be available on the KAUST VizLab YouTube channel. And for those of you who are joining live, of course, we're going to share that link to the KAUST YouTube channel with you, so you'll be able to watch this recording later on. Okay, so with that, I'm going to share my screen. Okay, so first I want to make things nice and big. So let's just make this side pretty big, and okay, and then I'll make this side also a bit bigger. Okay, so just quickly, so is that large enough, the text? So I'm going to try to have a split screen where on the right-hand side of my screen, I'm going to be doing the live demos and actually the coding, and then on the left-hand side of my screen, I'm going to have the teaching notes, and I'm going to try to keep things kind of split screen like this. So let me just take a quick look at the chat. Okay, no complaints. Reasonable. Okay, well, reasonable is good. Good enough. Okay, so here we go. So let's talk a little bit about Jupyter Lab and how to use Jupyter Lab before I kind of dive into the course material and what we're going to cover today. So we're going to use Jupyter Lab throughout the workshop series. For today, the only thing I want to talk about is the terminal. So we're going to be using this terminal down here. So if you click on the terminal, then you will get a terminal. And so this is the easiest way that I could think of to give a very large number of people access to a bash terminal, where I can teach you how to write bash commands and write shell scripts in a way that will work for everybody. So your computer, if you have a Mac or if you have a Linux computer, bash is already installed on your system. It's already there. You don't have to install anything. Windows users, there is a little bit of work that you have to do to install bash, unless you have a very, very new version of Windows. And so using these cloud resources, which are provided to us by the team at MyBinder and my colleagues here at KAUST, the Research Computing IT, who is providing the KAUST Binder Hub for those of us who are here working at KAUST. So big thanks to them, because without these cloud resources, it would not be possible for me to teach such a large group of people remotely like this. Okay, so over here, we're going to be typing bash commands like pwd and ls and things like this. And then we're going to get some responses to these commands, and I'm going to talk about what the commands mean and all of that, of course, in a little bit. But that's what I'm going to do. So we're just going to be working in this terminal. If you do something and you accidentally close this terminal, then you just click the terminal again, and you have a new terminal, and off you go again. Okay. Okay, so that's all we're going to talk about Jupyter Lab this week. In the following weeks, we're going to talk a lot more about Jupyter Lab when we get into building our data science and machine learning environments with software environments with Conda. And then when we start programming in Python, then we'll really spend a lot of time explaining how to use Jupyter Lab and what the different parts of Jupyter Lab do and things like this. Okay, but today we're talking about the Unix shell. And the Unix shell is the tool that I probably use the most, because for me, it is the entry point through which I talk to the computer. It has been around for a long time. And the reason that it has survived for so long is it allows you to do very powerful things with computers, things that you can't really do using a mouse and kind of clicking and dragging, the kind of graphical user interfaces that we're all used to using, or touch screens more recently. It allows you to do a lot of things with relatively few keystrokes. So there's going to be some simple commands and ways to combine commands to do more complicated things that we're going to talk about today. I think more recently, for data science and machine learning, the reason that the shell is so important is that it is the primary way through which you will interact with remote computing environments. So if you are a student here at KAUST, then you need to know how to use the bash shell in order to interact with the computing facilities that we have here, whether it's the commodity cluster IBEX or the supercomputer Shaheen. The same will be true if you're at a different university that has kind of centrally managed computing resources. It will almost certainly be accessed remotely using a terminal, and that terminal will almost surely run bash, or a close cousin of bash, maybe. If you're not at a university, if you don't have, or you're not at a company that has on-premise computing resources, if you want to use cloud computing resources, then you will also very likely have to be familiar with bash and be familiar with terminal commands. There may be things that you can do with GUIs with cloud resources, but if you want to get the most out of your cloud resources, you will need to access these resources using a terminal, and that terminal will almost surely be running bash. So the skills that I'm going to teach you today are kind of the core skills that you will need to kind of do a lot of bookkeeping and file management and things like that, and some job automation on your own computer, but will allow you to understand how to access high performance computers and big computing clusters, whether at your university or your company or in the cloud. Okay. So getting started. The first thing that I normally do would be, if I was teaching this workshop live, is I would go through the setup instructions. So I'm just going to open this in a new tab and show you. So again, if you want to install bash shell on your computer and the data files that we're going to use today, you can walk through the instructions here. There's a link and instructions for each operating system. For Mac and Linux, there's not much to do. For Windows, there's a little bit more effort that needs to be done in order to get bash, which is a Unix-based tool, installed on Windows, which is not a Unix-based operating system. But it can be done. It's not, it just requires a little bit more work. But the instructions for how to do that are all here. Okay, but as I said, we're not going to say anything more about that. Okay, so let's dive right into introducing the shell. Okay, so in this episode, which is going to be, I think, quite brief and less hands-on, I should say, than the other episodes, I'm just going to give a brief introduction to the shell. We're going to talk about what a command shell is and why you should use one. And then we're going to talk, I want you to come away from this discussion with an understanding of how the shell relates to the keyboard, the screen, the operating system, and the programs that are on your computer. And then talk about when and why command line interfaces, or CLIs, should be used instead of graphical user interfaces, GUIs or GUIs, which we're all very familiar with because they're ubiquitous today. Okay, so some background. We all have experience using GUIs. graphical user interfaces. So these are any way that you interact with the computer when you're doing kind of point and click or drag and drop with a mouse. So your browser is the classic graphical user interface, or like a standalone program where you open a program and you have a window and you click and maybe do some typing into a field and hit enter and then drag and drop files and things like this. So these are all different components of graphical user interfaces. So graphical user interfaces are very popular because they're quite intuitive to learn, because we humans are very visual creatures. And so the immediate visual feedback that you get from dragging and dropping, clicking, selecting, these are all things that that are very intuitive for us. But there is a cost to that. There's a cost to that, in that operations that you perform with graphical user interfaces don't scale very well. So if you have a very repetitive task, and you could do that using a GUI interface by dragging and dropping a file and clicking some buttons and then hitting enter, that might take you, I don't know, a few seconds to do. But suppose that you had to do that same process 1,500 times. Well, that would take you ages, and it would be really redundant. It would be really error prone, and it would be really boring, and not the kind of task that humans are typically good at. It'd be much better to find a way to automate a task like that with a computer. And the way that you automate tasks like that is by using command line interfaces, like the shell, which is what we're going to talk about today. So command line interfaces, or CLIs, and a scripting language like Bash are fantastic at automating repetitive tasks and making them go quickly. So with some of the commands that we're going to use today, we're going to see how to take a scientific workflow that could take many tens of hours to do, and show how it can be completed in basically just a few seconds with a simple Bash script. And so that's kind of what we're going to build towards over the course of the day, is building a Bash script to replicate a GUI-based scientific workflow, data analysis workflow, and show how it can be done much more efficiently, much more quickly, and much less without any errors using the shell. Okay, so what is the shell? So the shell is basically a program where users can type commands. And so over here in our terminal window, so we have our shell. So this is what I mean by the shell or a terminal. I'll use these phrases they mean the same thing. So in the shell, we can write commands, and one command would be, oh, what has happened here? I looked like my terminal has died. I talked too long and my Jupyter Lab died on me. So I need to go back and get another one. So this is what happens if your Jupyter Lab has died on you. You just go back to the GitHub repo and you click the Calst if you're here at Calst, or you click the public Jupyter Lab if you're in Jupyter Lab, or sorry, if you are outside of Calst, and then you can get back to where we were. There we go. So you can type commands into the Bash shell. When the shell is first opened, you see this blinking black and dot. So that's basically the cursor or the prompt. And another feature of the prompt is usually a $sign. So you can think of the prompt as being kind of the $sign followed by the blinking cursor. And at the prompt is where we type commands. Like I typed pwd, and then I typed another command, ls. We'll talk about these commands momentarily. Okay. So let's try our first command. So the first command that I want to teach you is a command called ls, which is short for listing. So this command is going to list the contents of the current directory. So, and that's, as you can see, what happened is that my current directory is has these directories and files here. So you can kind of visually see in the Jupyter GUI interface, you can see, just like you would in kind of like a file explorer or a finder on your own computer, you can see directories and files that are listed. And what you'll notice is that, make this just a little bit bigger for a moment, there, is that when I ran the ls command and then hit enter, I get the exact same things. Their sorting is a little bit different than how they're displayed here, which has directories alphabetically first, followed by files in alphabetical order. Here, everything is just done alphabetically, and we get some kind of color coding to differentiate things that are directories versus things that are files. But it's the same thing. So this is the command line equivalent to kind of opening up a file explorer on your computer, for example. So make that go away. So ls is just a basic command that's useful for finding your way or finding out what is in the directory that you're in. Okay, so what happens if you actually mistype a command? So instead of ls, if I were to type ks and hit enter, I would get an error like this. And this is the error that basically says the command ks cannot be found. So what bash has done here is it has interpreted your ks as being the name of some program or some command that you want to run. And it went off and tried to find this command ks on the computer, and it couldn't find it. And it came back and said, I cannot find this command. So that's the typical error that you will see when you make a typo. So I'll make many typos today, and so we'll see this error a lot. Okay, so I'm going to wrap up this episode with a kind of a motivation for the scientific workflow problem that we're going to talk about and use for the rest of today. So we have this fictional marine biologist, Nell Nemo, and she has just returned from a 6-month survey of the North Pacific Gyre. So the North Pacific Gyre is this big circular current, I believe, in the North Pacific Ocean, and the current collects a lot of plastic that that comes out of kind of the Asia Pacific region, and it gets sucked up into this big current and then creates this giant Pacific called the Great Pacific Garbage Patch. I believe it's about the size of the country of France. And it's just plastic. It's all the plastic that gets dumped in the Pacific Ocean eventually, because of these big currents, ends up in this garbage patch. So she's gone up there and collected about 1,500 samples that she needs to run through a physical machine. And this machine takes these physical samples, which could be like test tubes full of water or some other kind of physical sample, and it measures the relative abundance of these 300 proteins. So what she needs to do is take each of these 1,500 samples and run them through this assay machine in order to generate 1,500 files. And then once she has these 1,500 files, she's going to run them through some statistics program that is going to generate some statistical analysis or some data analysis. Then once that's done, she's going to have to write up a report on her results, and she needs to do it by the end of the month so that she can meet her deadline of submitting it to this fictional journal. Now so that's kind of what we want to do, and that's a very typical kind of program or type of workflow that scientists and data analysts encounter. You have some source of data. In this case, it's physical samples that are being run through a scientific instrument. And then that scientific instrument is going to generate some data, and then that data needs to be analyzed. And if you were going to do this kind of by hand using a GUI interface, you could do it because there is a GUI version of this program, but then you'd have to select a file, do some dragging and dropping, and you'd have to do that 1,500 times. And you might think, well, that's not hugely onerous. I could do that. It only takes a few seconds for me to drag and drop a file. But if the GooStats program takes 30 seconds to run on each file, and then it takes maybe a few seconds to do the drag and drop, you're looking at over 12 hours of Nell's, of a scientist's physical attention, because they're using a GUI to interact with the computer. So they have to sit down and physically do this dragging and dropping for 12 hours in order to complete all these 1,500 files. What we're going to see today is how to use the shell to automate this process. So instead of taking 12 hours, this takes minutes. And it's minutes of the computer's time, not of the scientist's time. So we're going to talk about how to achieve that. Okay.
Excuse me, Professor.
Yes.
Can you please zoom, because it's difficult for me to see. Maybe it's good for others.
Okay. So I will make everything, I think about, that's probably as big as I can make it and still have space. So I've made it a little bit bigger. Okay. Okay. So the key points that I want you to take away from this first episode is the idea of this this run, read, print cycle. So this is what we did when we typed our command like ls, and then the program was read by the shell, and then it was executed, and then the results were printed back to the screen. So we're going to be doing this a lot with all of our commands today. Most commands take options or flags that start with the dash. We're going to talk about this in detail in the next episode. But there are all kinds of different flags that you can pass in to the ls command to change the output. And we're going to talk about these momentarily. So tab completion. So I didn't demonstrate tab completion. So we'll talk about tab completion later when we have some more commands. And I guess the main advantages and the main disadvantages. So the main advantage of the shell is that you can get a lot done with relatively a small number of commands, which are very short. A disadvantage is that it's not as intuitive as a lot of graphical user interfaces, and the commands, when you're learning them, can be a bit cryptic. Like the fact that the ls command lists all of the contents in your current directory was not obvious to me when I first learned bash, when someone taught me ls. Like, there's nothing really about ls that screams this command is going to list a bunch of things in your current directory to me. So that's the trade-off. It's very powerful, but it's a bit cryptic. There's a learning curve, but then that's why you're here today. Okay. So let's go ahead and move on to the next lesson. So navigating files and directories. So this is one of kind of the core lessons for today. So we're going to cover a lot of commands in this lesson about how to navigate files and directories. So the three questions that I want you to be able to answer after we've gone through this material is, I want you to know how you can move around on your computer. So instead of using a mouse and clicking and using the Finder or the File Explorer to navigate through your file system, I want you to understand how to do that using the shell and some basic commands. So you're going to see how to see what files and directories that you have, and also how you can specify a particular location on your file, how you can specify the particular location of a file or a directory on your computer. Okay. So the part of your operating system that manages your files is called the file system. So file systems on computers are organized in a particular way, usually into directories or folders, and then files. And directories can contain other directories, but eventually a directory will contain 0 or more files. So the idea is to try to understand how can we explore these files and directories using the shell. And the first command that we're going to learn to do that is this command pwd, which stands for print your current or working directory. So if I were to type pwd and hit enter, then I get this home directory. Now, this is the home directory of the user in your cloud resources. So it's going to say Jovian for everybody. But if this were your own computer and you were to type this command after starting a new bash shell, it would say home and whatever your username is on that particular computer. Okay. And the home directory looks a bit different depending on what operating system you're on. Windows has slashes that are in the opposite direction of the slashes that you find on Mac and Linux. And some other things like that, but don't be too distracted by that. So just a bit more about the concept of a home directory, because it's quite important. So a file system is typically going to look like this on a computer. You're going to have what's called the root of the file system, which is kind of the root of this tree of directories and files. And then inside that root, which is represented by a slash, you have some directories. And one of those directories is usually a user's directory. And then you might have some other directories as well, depending on what operating system you're on. But there will generally be a user's directory. And then inside that user's directory might be only one user, if it's your own personal laptop or machine. If you have a computer that's managed by your company or your university's IT, then there will probably be multiple users in there, because your IT staff will have had to come in and use their usernames to do stuff on your computer. Or if you are logged into some remote computing cluster, there could be hundreds or thousands of users in the users directory, depending on how large your university is. Okay. So, and again, underneath users, you're going to have these many different user directories. Okay. So let's talk a little bit more about what is in our home directory. So if we run ls again, I seem to have lost my connection again, so I'll just start another one. I will try the pub binder hub this time. Except, whoops. I'm just going to wait a few seconds for this to load. I'll check the chat and see what was in the chat. Okay. Okay, here we go. And then I'll make this bigger again. And we'll get a terminal back. Okay, and we'll run the ls command. Okay, so our home directory looks a little bit different than what is here in the notes. What's here in the notes is what you would get if you were running ls on a Mac or a Linux machine generally. All of both Mac and Linux will typically have these folders in your home directory on that machine. Okay, so there are some options that we can use with ls. So if we use ls followed by -f, a capital F, so this is our first option, what we'll see is that the output has changed. So now, in addition to these kind of color differentiated kind of light blue or gray, denoting that these are directories, we now have a trailing slash to let us know that this is in fact a directory. So the color coding of your bash shell will depend on exactly how the system on which you're running bash is configured. So you might not have any color coding at all. So if you didn't have any color coding, then this is the best way to figure out what things are files and what things are directories with this -f. Okay. And there are some other things that we don't have here. That would be, instead of a trailing slash, you might get an @ sign, which indicates something called a link. And then a star would indicate a file that was executable. And we'll see some examples of those kinds of files later. So next command that I wanted to show is the clear command, which is really handy if your terminal just gets full with different commands and too much output and it's hard to look at. You can just type clear. And then get back your a cleared terminal. So that's very useful. And if once you've cleared your terminal, you can actually use the up commands and down, or the up arrow and the down arrow to toggle through the command history that you've previously typed. So that's really useful. So you don't lose those commands when you type clear. Okay. Just real quickly, so I know that it's not just me. Is anyone else having this problem where very quickly you seem to be losing the ability to type into your terminal window? And you have to constantly restart in the cloud computing resources. Okay, so I'm not the only one who's having that issue. Okay. Some people are not. That's good. I'm glad that not everybody is having the issue. Okay, cool. Just wanted to see if it was not, make sure it wasn't something on my local machine that I needed to potentially fix. Okay, so now let's talk about, so we've talked about a command like ls. We've seen an example of an option, the -f. So let's talk about the general syntax of a command using this ls command again. So the general syntax of a command is going to look like this. So you're going to have the name of a command, something like ls, followed by some options that change the behavior of that command, followed by another space, and then some inputs. Most commands require inputs. And so the input to the ls command is the path to the directory whose contents you want to list. And when we don't provide a path, the assumption is that you want to list the contents of the current directory. But if you were to provide a path, and if you recall that we said the trailing slash a single trailing slash represents, or forward slash represents the root of the file system. So if we pass that in as an argument, then the output will be different. So what we'll see instead is the directories that are in the root directory of the whole file system. Okay. Now, if we were to type something like ls-f and forget the space between the command and the option, then bash is going to interpret that ls-f as a command. And it's going to try to find a command ls-f, and it's not going to find it. So the spaces are very important, both the space between the command itself, the space, and then the options, and then the space between the options and then the input. Okay. So for example,
excuse me.
Yes.
Sorry, I'm trying to use my workstation, and when I use ls, I don't have the command bash at the beginning. Like if you typed it by mistake, then you got like bash colon ls not command not found. I don't have this bash.
So when you type ls, just ls by itself,
it just lists without. No, for example, if I put ls -f attached together, like I should have. Yes.
And yours basically just doesn't return anything.
Yes.
Okay. Well, so I'm not exactly sure how your workstation is set up. So it's going to be hard for me to kind of understand why you're getting a different output. But I wouldn't worry too much about it. It's not returning anything. I'm not sure why it's not telling you that that's not a command.
Sorry, what I mean is it's returning, for example, ls minus f, then double colon, command not found. I don't have this bash.
Oh, you're just missing this.
Exactly, yeah.
That's okay. Don't worry about that. That's like, that's completely due to the way that your bash is configured to show error messages. So that's okay. Not to worry about it. Okay. All right, so we've talked about that, I think, enough. So now what I want to do is, so, where did these options like -s come from? So to do that, we need to look at some help menus. So ls has a command --help. And what you'll see here is that the help menu is quite detailed. In fact, there are enormous number of options for this command. We used only, let's find -F. Where is that? We used only this -F. That's it. There are many other options, some of which we will see later today. In the course of my day-to-day work, I use the ls command all the time, and I've only ever used maybe 2 or 3 of these options, and we're going to cover those later. So don't feel like, oh my gosh, I have to master the ls command by looking at all of these options and understanding what they do. No, that's not how it works. You don't have to know all of these options. They've been added because at some point, someone who maintains this program, ls, found it useful to have an option for that, for all of these different things, but you certainly do not need to feel like you need to master them all. Okay, and now I'm going to type clear to just get rid of the help menu. So we're going to use that a lot, --help. So, and so here's what the help menu looks like. Okay, so some unsupported command line options. So we talked about the error that you get if you do something like this. But what happens if you provide a command line option that isn't supported? So you get a helpful error message like this. So you get the name of the command, ls, and then you're told that, oh, this J was an invalid option, and you might want to try the command that we just learned, --help, ls --help, to find more information. And if we do that, we can kind of scroll through here and see that there is no lowercase j option anywhere in here. Oh, so thus it's not a valid option. Okay, and I'll type clear to clear that again. The help menu is also sometimes called the manual pages. And there's some discussion here about man pages and accessing them, and that they're available on the web. If you want to look at kind of a web page that has these help menus, all of these help menus are available online. You can follow these links to the online versions of the help menu and kind of navigate through them if you don't want to navigate through them in the terminal like we've just been doing. Okay, so these are our first exercises. So what I want to do is have you take, let's see, what's the best way to do this? Yeah. So let's take 5 minutes, and I'll have you work on these exercises to get some practice on your own. So each exercise kind of has a question that it wants you to explore. So this first one is, what does the command ls do when used with the -l option? And then what about if you try to use both the -l and the -h? So what's going on? And then each exercise has a solution. And the solution you can access by clicking this arrow here. Well, I won't click this solution because I want you guys to do this exercise. You can also do this exercise as well. And you can see the solution by just clicking the down arrow and then unclicking it to hide the solution again. Okay, so let's take a few minutes, maybe 3 or 5 minutes, to see how you get on with these exercises, and then I will go through them myself together. So I'll stop sharing for the moment and just set a little timer for myself. Make sure I don't get off of time. And during these little breaks for doing exercises, it's a good time to ask questions. So if you want to ask questions in the chat or you want to unmute and ask questions, I will do my best to answer them.
Hi, I have a question.
Yes.
So it's probably a naive question. So what's the difference between bash profile and bash RC? Why do we have different files like that?
That is a very good question that causes a lot of confusion with users. It's not something that we were going to talk about today. It's a very, in some sense, it's not a naive question at all. It's a very advanced question because most people don't really ever really touch those files too much.
Okay.
So, but a very long story summarized, briefly. So when you open up a terminal to, well, let me see if I have actually, I should have, let me share my screen. Okay. So if I run ls on my home directory, so we haven't talked about the -a option, but it shows you all these hidden files. And in here, there is a bash RC file. And this bash RC file, and we can take a look at it. So we're going to learn this command cat later, but we can use cat to actually display the contents of this bash RC file. So this is a file which contains a bash script, which is loaded every time you open a new terminal.
All right.
So this bash.rc is a file that's loaded, and it just configures the way that your bash terminal behaves for what's called an interactive session.
Okay.
Now, the bash profile is the same kind of a file, except it's sourced only when you log in as under what's called a login shell, which is different than an interactive shell.
Oh, okay.
So there are basically two different ways of configuring the behavior of your bash terminal, depending on whether you are using a login shell to log into a remote system, or whether you're using a terminal kind of interactively on your laptop, your workstation, or in this case, a cloud provisioned resource.
Okay.
And that's a very deep topic that you could spend a whole hour at least talking about the intricacies of bash profile and bash RC. So it's not a naive question at all.
Okay. Thank you.
You're welcome. Oh, and there is my little timer. Let me check the, great question, Anas. So Anas asked in chat, why are there 2 dashes with help? So share screen. So many options have a short form and a long form of the option. So if we were to look at ls --help, then let's just as an example here. So let's do so let's do this one. So the option -a also has a long form which requires 2 dashes, --all, and it does the same thing. So for example, let's clear this out. So if I were to run ls -a and ls --all, I would get the same output. So it's basically, what's called 2 dashes is what's called the long form of the option. And it's usually like a complete word or words that describes the option. And then there's almost always a short option, which is usually a single character, like in this case, the A, and you use that with a single dash. But if you'll notice that some options only have either short form or long form. So for example, dash uppercase U and dash lowercase v don't have corresponding long form options. But dash uppercase R and dash dash recursive, those are, the dash dash recursive is the long form of the dash uppercase R. So this is one of these things between kind of the original versions of these commands often only had these single character options, but those were harder to remember. So they came in and they put these longer form options in to try to make it more understandable what's going on. Personally, when I write bash scripts that I think are going to be used by other people, I almost always use the long form, like dash dash recursive, when possible, because I think it's a little bit clearer to somebody who might be new to bash or looking at that bash script for the first time. They don't have to look up what all these single little character options mean. Okay, so let's look at this exercise together. So exploring more about the ls flag. So what does the command ls-l do? Okay, so it clearly lists the contents of the directory, but with a whole bunch of other additional information as well. And we can do dash dash help. Let's see what the help menu says for dash L. So we can go through here and we can find, so dash lowercase l has no long form of the option, and it says use a long listing format. So that's, again, not the most, I would say, helpful of help messages. What does a long listing format mean? So it lists kind of vertically all the files. It lists in the rightmost column, you've got the files. And then here you have a timestamp of when that file was last modified. And then here you have this column of numbers, and it's not really obvious what these numbers are. So I'll come back to this in a minute. And then here you have a group name, and here you have a username, and here you have the permissions. So permissions is something that we're not going to talk about today. It's actually covered in a more advanced shell course that I teach. And I'll point you to the teaching materials for that more advanced shell course that you can go through on your own that talks about permissions and what these things mean. But the permissions are how the files and directories and who can access them and who can read files and who can write files and directories and how all of that is controlled and protected. So that's what permissions do. And then this is the username and the group name of the owner of the file or directory. So then what happens if we do ls-l-h? So notice that it all looks the same except for this kind of column of numbers here that didn't have any units on it, now has units. And the H stands for, I think, human readable or something like this. So if we look at the help menu again, so human readable, actually that's the long form of the option. So it's used in combination with these other options to show, it's clear, and then ls-l, and you can either do -l -h like this, or actually you can put them all together and just a single dash and then a whole bunch of letters for your different options, kind of up to you. So this is the file size. And this allows you to understand kind of how big the file is. So like if you had a bunch of CSV files, so comma separated value files that were data that you were going to analyze, you could run this ls-lh command and see how big those CSV files were before you tried to load them. Okay. So I'll leave this exercise listing in reverse chronological order, and its kind of explanation as a homework, if you want to call it, if you guys want to go through it on your own, in the interest of time. Okay, exploring other directories. So far we've been using ls mostly to look through the current working directory, but you can actually use ls to look through other directories. So if we run ls, so let's look at the directory introduction to shell. So if we run ls and then we pass the name of the directory that we want to list the contents of. So, and you can actually use something called tab completion. So if you start typing just a few characters and then you hit tab, then the shell will automatically complete as many characters as it can until it finds basically multiple files or directories that match that pattern. And then you can keep typing characters until you find a unique, it's a way to kind of speed up, minimize your typing, minimize typos. So if we list the introduction to shell directory, then we'll see that this directory contains another directory called data. Okay. And again, we could use the same options. So ls-f, introduction to shell, and we'll get this kind of trailing slash to let us know that this is in fact a directory. And if we wanted to dig even further, we could do introduction to shell data. And then we can see all of the contents of that directory. So we can pass in this path that we want to list the contents of to the ls command. And we can use whatever options that we've learned or whatever options that we want. And we can list the contents of that directory. Okay, so next command. So now that we know how to list the contents of a directory, we need to understand how to actually change directories. So we want to move around on the file system. So we need to know how to change directories. So the command to do that is cd. So for example, if we were to run cd introduction to shell and hit enter, then we would now be in a new directory. We will have changed from the home directory into the introduction to shell directory. Okay. So now, another thing to notice about the cd command is it doesn't print anything. So when we ran the ls command, we got results. So we ran ls and then something was printed to the screen, some results were printed, but our cd command didn't do that. And that's because it basically just moved us to a different directory, and it let us know that we're in a different directory because now the prompt has changed. You'll see that instead of just this little tilde symbol here, which we'll talk about in a minute, we now have tilde/introduction to shell. So the prompt gives us an indication of where we are in the file system. Okay. Now there's a command that I've used before, but now I'm going to actually teach you, pwd. So if I type pwd, then this prints the current working directory. And so my current working directory is from the root of the file system. So this is giving a path from the root of the file system into home, into my username, into introduction to shell. And if I use the cd command to change into the data directory, just remind everybody. So if I run ls, there's a data directory that's in my current directory, my current working directory. I can use cd to change into that directory. And notice that there's nothing printed to the screen, but now the prompt has changed again. And now if I run ls, I can see all of the things that are in the data directory. And if I was to run pwd, I would see the current directory that I'm in. Okay, so these commands, ls, cd, and pwd, are really the core commands that you need to know to navigate around the file system. So I use each of these commands all the time. And they are probably the majority of commands that I use actually when interacting with the computer via the command line. Okay, so let's see, let's run some more practice. So ls-f, and so we can see kind of what files and directories are in this data folder. So this is like the data that was collected by our marine biologist that we talked about earlier. Okay, so let's suppose that I wanted to leave this directory and go back to the directory that I was in before, the introduction to shell directory. So if I try to do that, make this a little bit bigger now. If I try to do that, if I try to do introduction I get an error, no such file and directory. And that seems weird, right? Because I know that this exists. I was just in that directory. So why is it saying that I have no such file and directory? The reason is that when you use the cd command, you can only use cd to move down the file system. So you can only use cd to move into directories that are in the directory that you're currently in. So if I wanted to do cd, I could use cd to change into creatures or data or molecules or North Pacific gyre or writing. But I can't use cd to go up to a directory that's higher up in the file system, like introduction to shell, or as I'll talk in a minute, the home directory. So how does this work? What do you do? Well, the way that you move up the file system is using a special pointer to the parent directory of your current directory, which is ... So if you do cd space ... then you've moved up a level in the file system. And so now if I do pwd, I can see that I'm not in the data directory anymore. I'm in introduction to shell. And you can see that also in the prompt now says introduction to shell. And if I go up even one more time, cd ... then I will be back in my home directory in this case, which is represented by the character tilde. So that's really important. So cd space ... is how you move up one level in the file system, in a file system. Okay, so you might think, well, this ... is like super cryptic. Like, where did this come from? How did you know to do this? Well, if you run the ls command with the -a option, what you'll see is that every directory in the file system has two special, actually these are directories, two special directories, ... and ... And these directories are actually pointers to the parent directory and actually the current directory. And we'll talk about some use cases for the single dot later this afternoon. But for now, I'm just showing you the ... and kind of the motivation behind the ... directory. So you use it to move up the file system hierarchy. Okay, so these are the basic commands for navigating the file system on your computer: pwd, ls, and cd. Okay, so let's use cd. So if we use cd again to go back into our introduction to shell and then data. Okay, and we can use pwd to see that we're actually in that directory, and then we can do ls to see, again, what is in that directory. And so now what happens if we just type cd without any input? We just hit cd, enter. Well, what happened? Well, our prompt changed, which suggests that something did happen. And you can see now, instead of having introduction to shell / data, we just have this little tilde here. And if we were to type pwd to figure out where we are, you'll see that now we're back in our home directory. So no matter where you are in your file system, if you type cd and hit enter, that's going to basically take you back to your home directory. So it's a handy shortcut. Okay. So I think the last thing that we're going to talk about in this exercise or this episode is the difference between something called a relative path and something called an absolute path. Okay. So when we use dot and dot dot, we are providing relative paths. So if I was to do, so let's go down into introduction to shell, data, and creatures. Okay, so here's some data files in this creatures directory. If I was to do cd dot dot, I'm providing the relative path. So this is the path relative to the current directory to the directory where I want to go. So let's say that I wanted to go up to the just up to the parent directory. So relative to my current directory, I need to go dot dot to get to my the parent directory. Yeah. So then I can change directories back into creatures again. Now, if I didn't want to use the relative path, I could also use an absolute path. So the absolute path is a path from the very root of the file system all the way down to the directory or the file, or in this case, the directory where I want to go. So absolute paths are usually much longer, but they will uniquely identify a directory or a file starting from the root and going down the file system. So if I wanted to do the same thing using an absolute path, I would need to go from the root of the file system into, I think, home, then Jovian, then introduction to, I'm gonna make this quite wide again. Introduction to shell, and then data, and then, yeah, because I want to go to the parent directory. And now this is a bit of a mess, so I'm going to clear this out. So this was the command that I typed. Okay. cd creatures. Okay, so this was the command that uses the absolute path from the root of the file system all the way down to the parent directory of the creatures directory. So if I use an absolute path, I can accomplish the same thing. If I go back into creatures, but usually you'll end up using a lot of relative paths because once you internalize the idea of the dot dot as referencing a parent directory, then you'll find that that is often easier to use and shorter, certainly. Okay. One last thing, and then we're going to have some exercises. So the shortcut, so I mentioned the tilde. So tilde is another useful shortcut that stands in for the current user's home directory. So cd tilde is accomplishing the same thing as doing just cd without any input. Because the tilde represents basically the absolute path to the home directory. So it's a handy shortcut. So if instead of going to, so if I went to cd introduction to shell, data creatures, I could do cd tilde to represent my home directory slash introduction to, instead of shell, I think there's an introduction to Python. So I could use the tilde as a stand-in for my home directory, and then some other directory that I wanted to navigate to. And then this gets expanded, this tilde, bash substitutes in the absolute path to my home directory, which then contains introduction to Python. And then if I was to do pwd, then you'd see I'm in the Python directory. And if you did this, you would see the contents of the Python directory, which has all the stuff that we're going to look at in a few weeks' time when we do introduction to Python. Okay. So there are 2 exercises here. I want to take kind of, or 3 exercises actually. And then we will wrap up this and move on to the next episode. And I think probably after we finish this this episode, it would be a good time to take a longer break, like maybe a 15-minute break. Okay, so I'm going to, so please take a look through these 3 exercises, 3 or 4 exercises here, absolute paths and relative paths, and then kind of if you understand how to navigate around, and then we'll wrap up the episode. Okay, so I'm just going to set a timer real quick. Okay. And please feel free to, again, ask questions. Then chat, or you can unmute yourself and ask questions. Or I'll just sit quietly and drink my tea.
So we are having different files here in the exercises, right?
Yes, so in the exercises, let me share my screen again, just to make sure it's clear. So this first exercise, for example, is kind of testing if you understand these relative paths and absolute paths and how to use CD to change directories. So these files don't exist on your cloud computing instance, but it's asking you, like, if you were in this directory, so /users/Amanda/data, which of the following commands could you use to change and go up 1 level in the hierarchy to users/Amanda? So it's kind of testing all the things that we talked about, whether or not you understand what these different things are going to do. And then similarly here, you're given this like picture of a file system, and said, well, if you were to type the command pwd and it displayed users thing, so that would mean that you are in this directory, but in this directory here, then what will the output of this command be? So if you're in this directory and you were to run this command, then what would it display, basically? And then this one is similar, but maybe a little bit more advanced because it asks about this -r option, which you might have to look up in the help menu for the listing command, the ls command. Okay. So hopefully that gives you enough context for the exercises. Okay, so let's take a look at, let me share my screen. Okay, so let's take a look at, let's take a look at this first exercise. So absolute versus relative paths. So starting from user/Amanda/data. So if we were in this directory, this data directory here, which of the commands could you use to navigate to the home directory, which is just one level up from our current directory? So if I wanted to kind of set up something like this in here, I would need to go to the home directory and then go one level down. So let's suppose I went into the introduction to shell. Okay, so if I was in the introduction to shell directory, which is kind of one level below my home directory, so which of these would take me to the home directory? So now we can kind of test these. So if I was to do cd dot, that is going to take me to my current directory. So it's not changed, so that's wrong. cd slash has, where has that taken me? So that has taken me to the root of my file system, which is not where I want to go. So I actually want to go back to where I was. Jeroen, introduction to shell. If I do cd slash the absolute path to my home directory, then that will work. So that puts me in the home directory. Yep. So then let's go back to where I was, so introduction to shell. If I do cd dot dot to go to my parent directory and then dot dot again, where does that take me? That takes me to home, but actually where I wanted to be was in my own home directory, so home/Jeroen. So that's not right. So we go back to introduction to shell. So 5, cd tilde. So cd tilde will work because tilde is a placeholder for the absolute path, a shortcut to the absolute path to the user's home directory. And okay, and then so cd cd home won't work. So I have to go there. So if I try to do cd home, that's not going to work because there is no such file or directory called home inside the current directory, and that's not where I wanted to go anyway. If I was to do cd, so this one is really kind of goofy because it's saying cd tilde, which is the home directory where I want to go, but then down into the directory where I currently would be, introduction to shell, and then up to the parent directory. So that one actually works, but that's really like a convoluted way to accomplish something, and that's not what you would want to do. But if you understand why number 7 is a correct answer, then you understand the concept of the tilde as a placeholder for the absolute path to the user's home directory, and the concept of dot dot being a pointer to the parent directory. And again, the last two are the most, I think, the common ones that you would find people use to go up one level in the file system. So let me just clear this out. If you would use cd with nothing, so that always takes you home. So that's great. That's what I do. If I want to go home, I just do cd and hit enter and go to my home directory. And then if you want to go up one level in the file system, you just use ... to go up one level in the file system to the parent directory, which in this case is the user home directory. Okay. Ooh. So there's some more explanation here in the solution. And again, like if you understand the answer to this exercise, then I think you have a good understanding of both absolute and relative paths, but also how to move around in the file system. So the other two, I'm going to leave you to go through the solutions on your own in the interest of time. And then I want to finish this up, and then we're going to take a break. Okay, so now we know how to move around in files and directories. So let's talk about the data that we're going to be analyzing. So we're going to change into the introduction to Shell, into the data, and okay. Here we go. Okay, so we have a directory called North Pacific Gyre. So if you were to list the North Pacific Gyre directory, we'll see that it has a, there we go. We'll see that it has a single directory that has a date, 2012-07-03, which is the date that she started processing the samples. And then okay, so each of the samples is actually stored in this directory. So if we do ls North Pacific Gyre 2012, make this a little bit bigger so that, okay, so I changed that directory, and now if I run ls, okay. So, and let's do lsaf. Okay. So in this North Pacific Gyre and then 2012-07-03 directory, I have all these text files. So these are going to be the text files that are kind of have been generated as output from the physical machine, the scientific instrument that we put fed the raw samples into. So these are the files that we want to understand how to process in some kind of an automated fashion. Okay. So what we're going to do is, and the rest of the afternoon is talk about how to use bash to automate the process of processing all these kind of text files, and then learn a bit more about a few more bash commands and things like that along the way. Okay, so some key points to wrap up. So the commands that we covered again were cd, which changes the current working directory from the current working directory to the directory whose path that you specify. The ls command, which lists the contents of a directory whose path that you specify. pwd, which prints the current working directory. So those are the commands. And then we learned a bunch of shortcuts, like / is a shortcut for the root directory of the whole file system. The tilde was a shortcut for the path to the user's home directory. ... means the directory above the current one, and then dot means the current directory. So some things to remember. Okay. So what we're going to do now is we'll take a break. And we'll reconvene. It's about 2:43, so let's reconvene at 3 o'clock. So that's a 17-minute break to get some tea or coffee, or I'm not sure what time prayer time is today, but this might be a prayer break for some people, or just to relax for a little bit. So I'm going to pause the recording now, and then we'll resume the recording at 3 o'clock when we start up again. Okay. Any last minute questions before we break? Nope. Okay. All right. Well, I'll see you again in about 15 minutes. So 3 o'clock. Now. Okay. So welcome back. I hope you had a nice 15-minute break or so. So now I'm going to pick up the pace a little bit. So I always kind of start this workshop a bit slow, in part because the shell is usually a very new environment for many people who are attending this workshop. And I want to just really kind of go slow and make sure everybody kind of stays, that we all stay together and we all understand what's going on. So now I'm just going to kind of pick up the pace a little bit for the rest of the afternoon and try to get as much material covered as we can before we're done in 2 hours from now. Okay. So let me share my screen. Okay. And let me see if I still have my binder instance or not. It looks like I do. Okay. So working with files and directories. So this is now episode 3. So we're going to talk about how to create, copy, and delete files and directories. So the next kind of important bit of material. And then we'll talk about how to edit files. And then the idea is that by the end of this, once you know how to create, copy, and delete files and directories and how to edit files, you should be able to create a collection of directories or a hierarchy of directories that matches a kind of a given diagram. And then create files in a hierarchy using an editor or by copying and renaming existing files. And then how to delete, copy, and move around specified files and directories. Okay, so let's see where we are. So we are in this, this directory of data, and we want to go back to our introduction to shell/data directory. So that is 2 directories up from where we are. So the easiest way to do that would be to do cd ... to go to the parent directory / ... to go up one more level in the hierarchy. And make that a little bit bigger. So there's the command ... /... And then if you look at where we are, you can see that we're now, we've gone up 2 levels in the hierarchy. And so we're now in this data directory, which is where we want to be. And if we run ls-f, so now we see roughly what is here in the notes. Okay, so let's see how to create a directory. So to create a directory in the current working directory, we use a command called make-dir. This is actually one of the more reasonably named shell commands because make-dir kind of sounds like make a directory. And the name of the directory we'll make is thesis. So now if we run ls-f again, we see that we've created this thesis directory here. And if you remember, there was another option for the L command -L. And so we can see that here's the directory that we just created, this timestamp. And so this timestamp was today's date and 12:05. So this machine must be like UTC or something like that. So we're, I think, I'm here in Jeddah, and then that's about 3 hours ahead of UTC, I think. So, okay. So if we were to run ls-f and then thesis, the directory that we just created, we'd see that there's nothing there, which is not surprising. We just created an empty directory. So something else that you can do is you can create many directories at once, a whole like subset of directories. So we could do make-dir with the -p command. And then we could say, well, let's make inside the thesis, we'll make a chapter 1 directory. Maybe we'll do chapter 1 directory, and then a section 1 directory. And you could go one level deeper if you wanted. I'm not going to, just to not have my command overrun the space on the screen. Notice that I used a dash instead of a space. So you want to avoid space in file names. That creates problems, in part because spaces are used as delimiters in bash commands. So here we have the name of the command, make dir, followed by a space, followed by options, followed by space, followed by input. And then if we have a space in our file name, then bash is likely to interpret this as the end of some input followed by a space and then some more input, which is not at all what we intend. So I tend to use dashes instead of spaces when I'm making file names. You can also use underscores like are used here in the lecture notes, but don't use spaces. Okay, so if we run this command, now if we list the contents of the thesis directory, we'll see that there's a chapter 1 directory. And if we were to list the contents of the chapter 1 directory, we'd see this section 1 directory we just created. Okay. So the make dir command is just another way of doing what you normally would have done with maybe a mouse, like a right click, create new folder or something like that in your Finder on Mac or File Explorer on Windows. So you are doing the exact same thing as what you would do with a GUI interface when you run this make dir command. Okay, so there's a call out box here. This yellow box here is kind of like a tip or a trick or a recommendation on good names for files and directories. So the first is don't use spaces. The second is don't begin names with a dash. And the reason for that is, again, in bash commands, dashes signify options. So if you wanted to create a directory called -p, a directory that started with a dash, then a bash command is likely to interpret that as a whole bunch of options, which isn't what you intended. If you have to refer to names of file directories that have spaces or other special characters, which sometimes happens, then you can put things in quotes. So, for example, if I wanted to do make dir p, and in the thesis, I wanted to do chapter 2, then you could put this in quotes. And then if you list the thesis directory, then you'll see that there's chapter 1 and chapter 2. And then when we learn the remove directory command, I'll come back and delete that chapter 2 directory. But you can put things in quotes if you, I mean, again, don't use spaces in your file names, but if you needed to deal with a file name or a path that had a space, then you can put double quotes around it and handle it that way. We'll see some more examples of that later today. Okay, so let's talk about how to create a text file. So I'm just going to clear this. So let's cd into our thesis directory. Okay, and so now we're going to create a text file. So there's a couple of ways that we can create text files. If you are, and we're going to focus today on how to use the terminal. So we could go and use Jupyter Labs GUI capabilities to create a text file inside this thesis directory, but we're not going to do that today, because today the focus is on learning how to use the terminal to do these kinds of things. So we can use a program called Nano, which is a very simple, well, simple is not the right word. It's a command line based text editor that has the basic features of a text editor, but not a lot of advanced features that you might be used to if you have written a lot of code and you have your own favorite text editor. Okay, so Nano. So Nano is installed already for us. If you are, Emacs and Vim are two, widely used text editors, but they have a fairly substantial learning curve. And to be honest, like they're, I think the most widely used text editor, certainly the one that I use, is Microsoft Visual Studio Code, which is free. It works on all operating systems. So if you don't have a favorite text editor, then I would recommend that you take a look at Microsoft Visual Studio Code. Yeah. So here we go. You can download it. It has all the features that you might possibly want. It's free. Highly recommended. But we're going to use Nano today. So if we type Nano and then the name of the file that we want to create, it's called draft.txt. Okay, so now we're dropped into this, what's called a buffer. And this buffer is basically a place for us to type text into a file. So we'll type, I'll just type what's in the lecture notes. So it's not publish or perish anymore. It's share and thrive. Okay, and hit enter. Now, at the bottom of the buffer, you see some keyboard shortcuts to do things like exit or write out a file or cut text, uncut text. So these are the kind of command line shortcuts that you can use. So what we want to do is we want to write out the file because we're saving the file effectively. So we do this by hitting the control button and Control and O for write out file. And when we do that, notice that it had file name to write and it's automatically put draft.txt. And we could either, if we didn't want to do this, we could hit Control and C, which corresponds to cancel. So I canceled, and note it said cancel down here at the bottom. So if we do Control and O, and now if we just hit enter, we have saved the file. And notice that we're still in the buffer. So we basically like saved our progress, but we haven't actually left Nano. And now we can hit Control and X to exit. And now we're back to our prompt. So we've created a file, added some text, and come back to the prompt. Okay. So now if we run ls on the thesis directory, we have these two directories that we created earlier, plus this draft.txt that we just created. Cool. Okay. So in the interest of time, I'll just kind of quickly move through this exercise. We'll do it together. So another way to create a file, instead of doing nano draft.txt and opening up a new window where we want to type some things, if we just want to create a file, but we're not ready to put any content into the file, we can use a command called touch. And we'll just touch file.txt, myfile.txt. Now, if we run ls-f, we can see that we've created this myfile.txt. And if we look at, so let's list the contents of the directory, but we'll do it in long form with human readable file sizes. So what you can see is that the draft.txt is 64 bytes. So it has 64 bytes of data. The my file.txt has 0. So its file size is 0. So that's how you can see that this touch command that we used just created a completely empty file with no content. Okay. And just a reminder about, so what's in a name? So the callout box is kind of reminding you that file extensions are more conventions that are widely used to indicate to humans what is actually in the file. So we use .txt to indicate that something's a text file, a .pdf to indicate that it's a PDF file, PNG or JPG for images typically. But a file is just kind of a collection of bytes. And a computer program, when given a file, will either understand how to interpret those collection of bytes or not. And just changing the extension does not in any way change the contents of the file. So you can't like convert a picture of a whale that has a .png extension that you could open with programs that understand how to read image files. Just changing that to an MP3 is not going to magically turn it into a recording of a whale song. But because computer programs will sometimes assume these conventions, an MP3 player might try to open a whale.mp3 file, and if it was actually an image that you just changed the extension on, then the program would crash. So the extensions are just conventions. You should follow them, but changing the extension isn't going to magically change the contents of the file. So just want to make that clear. Okay. So now we're going to talk about moving files around. So let's go up one directory level in the file system. So back to our Introduction to Shell data directory. And so let's move. So we created this draft.txt, and it's not really a draft of the thesis so much as it is like some quotes. So let's rename this file. So to rename, we can use something called the move command, which we'll use to move thesis/draft.txt to thesis. Make this a little bit bigger. To thesis quotes.txt. So when we run this command, now if we look at what is in the thesis directory, the draft.txt is gone and it's been replaced with this quote.txt. And here I've made a typo because the file was supposed to be quotes.txt, so we can practice this move command again. We can just move quote.txt to thesis quotes.txt. And now if we list the contents of the thesis directory, we can see that so this move command can be used to rename a file. So one of the things that you have to be careful about with this move command is that it will overwrite existing files with the same name, which could lead to data loss. So you can use this -i flag or option or -- interactive, which will make the move command confirm to you that you want to overwrite a file before overwriting it. Okay. So we saw how to use move to rename things. Let's see how to use move to actually move a file. So let's suppose we want to move the thesis quotes.txt to the current working directory. So we can represent the current working directory with a dot. And so now if we run ls on thesis, we'll see that the quotes.txt is gone. But if we run ls on the current directory, we'll see that the quotes.txt has been moved here. Okay. Okay, so this is a good exercise for you guys to do. So let's take a couple minutes and just have a look at this exercise and see if you have understood how to use the move command to move some files, sucrose.dat and maltose.dat into the wrong folder. So these are the commands that are providing the output of the files that Jamie sees. So listing the contents of the current directory gives you these analyzed and raw, and then listing the contents of the analyzed directory, you get these files. And then Jamie changes directories into the analyzed directory. So these are the commands that Jamie has run. So what would you need to replace in the blanks here to move these files, sucrose and maltose.dat, into the raw folder? Okay, so take a couple minutes and have a think about how you would need to fill in the blanks here, and then we'll talk about it. And please feel free to ask questions. So yes, Farouk, it is possible to move multiple files in one command line. In fact, that is an example of that is going on here. So the command is move, and then you're given this space separated list of files that you want to move. And then at the end, you have to kind of specify the path where you want to move those files. And Linda has asked the question, are we going to cover shell scripts today? So it is my hope that we will get to shell scripts today. So that's what I'm hoping for. And I'm going to try to make that happen. If it doesn't happen, then the shell script material is there, and then you can look at it on your own. And then the advanced teaching materials has quite a lot more on shell scripts, and I'll point you towards those as well. But hopefully, we'll get to the shell scripts today. Okay. So share screen. Okay, so just to see the solution. So this is an example of actually what Farouk was asking. So you can use move to move multiple files. So here we're using move command followed by space and then a space delimited list of files that we want to move. And we want to move them from the analyzed directory, which is where they have been mistakenly put, to the raw directory. And we do that by referencing the relative path to the raw directory, which we provide by .. /raw. Because .. in the analyzed directory, we have to go to the parent directory and then down into the raw directory to move those files. Okay, so copying files and directories. So the copy command works very much like the move command. So let me just clear this out of the way. Instead of it copies a file, but instead of moving it, basically. So we can provide, and we can check basically what we've done using the ls command. So let's suppose we want to make a copy of the quotes.txt. So we're going to copy our file quotes.txt, and now we're going to copy it to a file in the thesis directory called quotations.txt. Okay, and when that's done, we can actually use the ls command to just check that we've made a copy. So if we try to list quotes.txt and thesis quotations.txt, then these files are returned. So you can use the ls command to list a file to see whether or not that file exists. Alternatively, we could have done thesis or ls on thesis and ls on the current working directory. And then that now gives us the contents of the current working directory here, which includes the file quotes, and the contents of the thesis directory here, which includes the file that we just made a copy of called quotations. Cool. Okay, so if we want to copy an entire directory, like you want to make a backup of your data directory or a backup of your thesis, then we need to use the -r command or the -r option for help for a copy. So if we use --help to go and look at the copy command, we can go through here and find copy directories recursively. So there's -R, -r, or -- recursive. So this will copy a directory and then recursively go and copy any subdirectories and go and copy their contents all the way down into a file. So it's basically a way to copy an entire hierarchy of directories in a file system. So we'll do copy -r for recursive, and we'll copy the thesis directory, and now we will copy it to a directory which we will call thesis backup. And now if we run ls on our directory, so here's the thesis directory and the thesis backup directory. And we can check by providing, again, multiple directories that the contents of these directories are the same. So it is indeed a copy. Okay. So let's take just a couple of minutes and have a look at these exercises here. So the first one on renaming files, and then the second one on moving and copying. Okay. So I'll set my timer again. Okay. And then we'll just take a look at those exercises. And please do ask questions. So I know it's hard in these kind of virtual training sessions to get a lot of interactivity and a lot of feedback going between myself and you guys who are participating. But asking questions is a great way to both get more out of this training yourself, but also to provide more value to others, because I'm sure if you have a question, you're probably not the only one amongst the participants who also has that question. So don't be shy.
Excuse me, can you please repeat, how did you copy a directory?
Sure. So copying a directory, you use the -r for recursive. So let me share my screen again. So the example that we gave here is, so the copy command followed by the -r, which is short for recursive. And then this is the name of the directory that we wish to copy. And then this is the name that we make up, which is going to be the directory where the contents will be copied to. So this directory likely doesn't exist because we're creating a copy. So we just called it thesis backup, but we could have called it whatever we wanted.
Thank you.
So Vasim asks a question in the chat, can we copy into a different directory? So what I think that you mean by that, Vasim, is, so the short answer is yes, absolutely. Because the arguments that we pass, so let's give an example of this. So let's suppose that, well, I'll just do a graphical example. So if we go over here and so let's suppose that we wanted to copy this thesis, instead of copying it into the current directory. Yeah, we want to copy it into, as a timer for the exercises, we want to copy it into our introduction to shell directory. Yeah. So the way that I can do that is I can do copy recursive, the name of the directory I want to copy, and now I'm passing in either an absolute path or a relative path to the directory where I would like to make the copy. So let's suppose I wanted to give a relative path. So instead of copying it into the data directory, I want to copy it into the introduction to shell directory, so the parent. So then I would say copy -r thesis ... thesis backup. So now I'm providing kind of the path to where I want to create the directory and make the copy. And when I do that, then over here, you'll see here's this directory that I just created. And you can see that it has all of the same structure in it. So that last option that you're providing, or the last input that you're providing to the copy, is where you want the directories to be copied, basically. Okay, good question. Okay. So we have one more question in chat, maybe. Let's see. All right. So let's look at, all right, let's look at this one. So moving and copying. So what is the output of the closing ls command in the sequence below? So if we run the command pwd, and then if this is the output, so we're in a data directory inside Jamie's home directory, okay? We run ls, and the output is proteins.dat. So in that data directory, there must be a single file called proteins.dat. And then if we run this sequence of commands, then what is the output of the ls command at the end? Okay. So remember, we're in the Jamie's home directory /data. So if we do make dir recombine, that's going to make a directory called recombined inside this directory. And then if we run this move command, proteins to recombined, it's going to move this file from this directory into this directory that we just created. And if we run then this copy command to copy the file recombine proteins.dat to dot, so the parent directory of this directory, and save it as protein save.dat, and then run the ls command. So what we will have then in the current, and then this directory is only this directory that we created. So I think the answer is 2. Yeah. So this first answer is wrong because this file was first moved into this directory and then copied to the parent directory, which in this case was user home. And then this one is wrong for the same reason. And then this last one is wrong because this file was actually copied not to the current directory, but to the parent of the current directory. Okay. So if you think like, wow, these exercises are like a little bit tricky and they're kind of seem like they're designed to trip you up. So one of the cool things about being involved with the software and data carpentry is that instructors like myself are provided with a lot of training and instruction on how to not only provide training, but also how to create assessments which are designed to test common misunderstandings for new learners. And so each of these exercises has been kind of very intentionally designed to kind of test whether or not you are understanding the different commands that we're talking about. So they're supposed to be challenging. And if you find yourself kind of understanding the exercises and be able to do them, then you should feel confident that you understand the important takeaways from these lessons. Okay, so we talked about moving, we talked about copying, and now we're going to talk about removing or deleting. Okay, so let's remove this quotes.txt file that we've kind of copied and whatnot. So we had this quotes.txt file, which at some point we moved into the current directory. So let's remove it. So the way that we remove it is by using the command rm. So rm quotes.txt. And now if we run ls, we can confirm that this file is gone. And if we were to actually put the name of the file, ls would tell us explicitly that there's no such file or directory. Okay, so an important thing about deleting on with remove is that deleting is forever. So there's no trash bin or recycling bin or garbage can. When you delete something with the rm command, you are literally freeing up the memory on your computer where that data is stored. And then depending on the way that your operating system manages its free memory, that memory could be immediately reclaimed and overwritten with stuff, or maybe it won't be immediately overwritten, but it will be collected after a short period of time. So, so basically use with caution the rm command. So one way that you can use the rm command safely is with this -i flag or -- interactive. So if we do rm and help, we can see that there's this -i for prompt before every removal. And then there's some more options that you can apply even with the -r. So let's clear that out. So for example, if I tried to remove with the interactive flag from my thesis backup, the quotations text file, it will prompt me, it will say, do you want to remove this regular file? Yes or no. And you could say, well, actually, no, I don't want to do that. And then that file will not have been removed. And if there were more than one file, it would prompt you for, if you tried to delete more than one file and at a time, it would prompt you kind of for each of those files, whether or not you wanted to delete them. Okay, so what if we tried to remove a whole directory? So what if we try to do this? Well, remove, because it's such a powerful command, it kind of protects users from common error patterns. So it will not allow you to remove a directory that is not a non-empty directory, basically. So this thesis directory had information in it, had content, had data in it, so we couldn't just remove it with the rm command. We had to, and this is a protection, because if we accidentally just ran this rm command and just deleted our entire thesis and had no backup or no way to access it, like that would be bad. We don't want to do that. Okay, so in order to remove, another way to think of it is that RM will only remove individual files. If you want to remove multiple files or directories, then you need to use the -r flag or option. So the rm-r will recursively remove the directory that you provide, plus any subdirectories and subdirectories and subdirectories and so on down to the individual files, and it will remove all of those. So that's kind of how you would entirely delete a directory. But again, so if you do something like this, so now that thesis directory is gone, the entire thing. Notice there was no prompting or anything. So you can see it's gone. So it's a good thing that we backed it up, because we'd be in trouble otherwise. So from our backup though, because we've known we understand the copy command, we can actually back up our thesis, and we can copy our thesis backup to thesis and recover I forgot the -r for recursive copy. And now we've recovered our thesis. So this is a created example, but shows you how if you are both properly backing up your work and these basic Unix commands, even if you accidentally delete your thesis, you would be able to recover it very quickly. So to see what the interactive flag would look like, so if we did this command, but we added an I in there for interactive, then it's prompting you, do you want to descend into the directory thesis to remove stuff? And I would probably say, oh, no, I didn't mean to do that at all. So I just say no, and then nothing has happened. So we can still see that. The information is still there. Okay. So here's another exercise. I want to do this. Exercises. Okay. So what I want to do is so we're going to talk about operations with multiple files and directories, and then I'm going to leave these exercises because we've got about an hour and 15 minutes left. And so I'm going to leave these exercises and their solutions for you to kind of go over on your own. And then I'll skip ahead to the next episode. So, but let's talk about multiple files and directories, because there's already been a question about this. So typically, you don't just want to copy like a single file, you want to copy lots of files, or you want to remove lots of files, or you want to move lots of files. And so how can we do this? So let's talk about this here. I'll just kind of go through this exercise and show you how this works. So we're going to make a directory called backup. So we then created this directory here, and then we're going to copy some files. So we're going to copy amino. Where are we copying this from? Oh, no, I'm in the wrong directory. So let's remove the backup directory that we just created. So actually, we want to be in the data/data directory. There we go. So here are these text files, this amino acids.txt and the animals.txt. Right. Okay. So now if we make dir backup to create a backup directory, then I guess let me clear this. And now we can copy the amino acids and the animals into the backup directory. So this is an example of copying multiple files into a directory. So we list, separated by a space, all the files that we want to copy, and then they will be copied to this backup directory. So if we do ls on the current directory and the backup directory, you'll see that. So here are the files that we copied, and we copied them to this backup directory. Okay. All right, so there's an example of that. So, and so this was an example of copying multiple files into a directory. But if we actually try to do something like copy, because the copy command assumes that the last input is a directory where you want to copy the files. So if we try to do animals.txt and morse.txt, we would get an error because the expectation with the copy command is that whatever this last input is a directory, and morse.txt is a file. So instead of doing something weird like trying to copy these two files into a file, it just fails and says that this target is not a directory. And again, if you looked at the help menu for this, you would see that the usage for the copy command is like this. So the expectation is that either it's source and a destination, or multiple sources followed by a directory into which you want to copy those files. Right. Okay. So one of the things that you can do is use wildcards. So we'll see some examples of this. This is really useful of how to use wildcards to instead avoid typing out long lists of things. You can use pattern matching to identify files that you want to copy. So inside, let's go up one. Okay, so inside the molecules directory, there's all of these files that have something followed by a .pdb. So you can use pattern matching to, for example, list in the molecules directory all the files that end in .pdb. Or you could list all the files that start with a P and have any number of characters and end in .pdb. Or you could use, so the star is a wildcard that represents one or more characters, 0 or more characters. And then there's a question mark, which matches exactly 1 character. So if you said list all the files that start with something, a single question mark, and then end in methane, then you would get methane, because that's the only one that matches that pattern. So we can use these kinds of pattern matching all over the place. We can use the pattern matching to say, copy all the text files, all the files that end in .txt to some other directory, or copy all my PDF files, or things like that. And we'll see some examples of that in the following episodes. So these exercises are left for you to kind of go over, because what I want to do is move on to the next episode. So I'm really trying to get to the shell scripts, if possible, today. So the commands that we covered in this episode were copy, make dir, move, and remove. And we saw some pattern matching just now on how you can use star to match 0 or more characters in a file name, like star.txt to match any text file, or any files that end in .txt. And then the question mark, which just matches a single character. Yeah, so I'll leave it at that. So any questions about what we just covered in this episode before I move on to the next one?
Sorry, just a small question, please.
Yes.
If I've got like several folders, and I'm looking for a file, and I forgot where is the file located in these folders. How can I get hold to that file?
Okay, so there's I'm trying to think. So there is a episode on finding things, which we will probably not get to today. But the answer to your question, I could come up with some answer based on the principles that I've already showed you to try to solve that problem, but actually the best way to solve it is covered in this episode 7. So I would encourage you to just look at episode 7. I doubt that we'll get all the way through there today, because shell scripts is usually about as far as I get. But that's where the answer to that question is. Okay.
Yes, thank you.
You're welcome. Okay, cool. So then, I realized, so I wasn't sharing my screen. So when I didn't realize I wasn't sharing my screen. So what I was referring to was this episode here, Finding Things, if that wasn't clear. So in the Finding Things, you will see commands for finding. Look, the command is grep, but you can, explanation of what grep does and how you can use it to find not just like files, but actually text inside of files, if you need to. So, but we probably will not get there today. Okay, pipes and filters. Let me make this a little smaller. Okay, so pipes and filters. So here we're going to cover a really important principle of Unix shell commands, and a principle that has been deeply influential in software development in many programming languages, up to and including some of the most modern kind of parallel programming languages. And that's the concept of pipes and filters, and how to use something like a pipe to connect different commands together to create pipelines that process data, sometimes in parallel. So we're going to learn how to take these simple building blocks that we've learned so far and see how they can be connected together like little Lego bricks to build ever more complicated data analysis pipelines. Okay, so we're going to see how to redirect some command to a file, how to construct pipelines with multiple stages, and then talk about this kind of small pieces loosely joined philosophy. Okay. So we're going to see how to combine all of these things together. So we need to be in the introduction to shell data folder, I think. No, sorry, we need to be up one. Yeah, because we need to be, we're going to look in this directory. So if we list the contents of the molecules directory, we have all these .pdb files. Okay, so let's go into the molecules directory. And now let's use a program called word count. Bigger. And pass in the name of a file. And we'll just use Kube. So this word count program will go through a file and basically count the number of lines in the file, the number of words in the file, and the number of characters in the file. And so the word count is the name of that command. So, but what if we wanted to count all of these PDB files? Well, we could do word count star.pdb. And then it will count all of the files for us. So, and this word count program, we're using it because, not because it's like the world's most useful program. We're using it as an example. So if this is some statistics program that you need, that processes basically from the command line, processes individual files, then you will be able to use that program followed by star.pdb or star. Whatever extension your data files are in. And that program will be executed one after another on each of these individual files. So it's a general pattern that I want you to be mindful of. So if we wanted to just count instead of the number, if we just wanted to count the number of lines in a file, which is something I often do on data files that I work with. So PDB. So this gives us the number of lines in the file, in each of the files. So it's basically cutting out just this first column here. Now, I often use this command when I'm just starting an analysis. For example, I worked on a project with the Saudi Electric Company where they brought me all these data files that were raw CSV files. And I had no idea really like how much data was in these CSV files. So one of the first things I did was I ran this command. The command I actually ran was wc-l star.csv in the directory where I had all these CSV files. And it came back and told me basically how many rows were in each of these CSV files. And so I had some idea of how many data observations I was going to have to work with. So even this simple word count program can be quite useful in okay. So one thing that sometimes happens with commands like this is if you do something like word count -l and then you accidentally hit enter and you've not provided any input, then you think, well, what is going on here? It's like the cursor is just sitting here and not doing anything. Well, it's actually waiting for you to type some input. So it's a way of providing input directly to the command line rather than providing file. But typically this isn't what you want to do. And actually you just hit enter too early. And so you can hit Control and C and cancel the command. Okay, so we ran this command and the output was only 1, 2, 3, 4, 5, 6. So it's like 6 lines long. But what if you had a directory that contained like, that contained, you know, 1 million files or something like this, which is not unusual. We have many bioinformatics and genomics researchers at CALS have directories that have millions of files in them like this, and they have to process these files. So if you were to run this command, and if this pattern star.pdb returned 1 million files instead of just 6 or 7, then your screen would be streaming all of this input and you wouldn't have any way to like really do anything with it. So instead of streaming it to the screen like we've been doing, we're going to write it to a file. We're going to redirect it to a file. So we're going to run that same command again, except now we're going to provide a greater than symbol, or it's better to think of it as like an arrow. And we're going to put in the name of the file, into which we want to redirect. Sorry, get my. So we ran this command. And so we can see now we have this length.txt. And I've made a typo again. So we're going to use practice our move command to move it from length.txt to lengths.txt. So we can see that we've done that. So there's our lengths.txt now. Okay. Now, we want to look at this lengths.txt file. So there's a new command called cat, which we can do, we can use to actually just dump the output from the text file to the screen. So here we ran this command that redirected the output of this command to a file. And now we've basically just dumped the output of the file to the screen using this cat command. Okay.
I have a question here.
Yes.
So when I do cat for very long files, so sometimes in my terminal, I cannot go much to the beginning of the file when I do the cat.
Right.
So can I just cat the initial part of the file or something?
Yes, so we'll see that in a minute. But what you could actually do, there is a command called head, which will allow you to look at the first like 5 lines of a file, or the first line of a file.
Okay, thanks.
So, and also there's one called, we'll see it in a minute, but there's one called tail, which does the opposite.
Oh, okay, thanks.
There's some discussion here that's kind of related to that, which is that if you do cat on a file that is like huge, you might end up with like more output than what will fit on the screen. So there's another command called less, which does things that are similar to cat, except it will only display the information kind of like one screen at a time. And then you can kind of toggle through that file. So if I want to look at the contents of a large file, then I would use the command less, and then I don't know, let's just look at one of these PDB files. Yeah, okay. So then the less command, there's only one page of data here. And so it's showing me the one page. But if there was more, then I could use the space bar to toggle through the pages and pages and pages. Or I could use the B command to kind of go back to the beginning, and then Q will quit and take me back. So typically, if you want to look at the output of a very large file in the terminal, you should use less. But if you just want to look at the first few lines, then you would use head or tail to look at the last few lines. And we'll see that in a minute. Right. So I'm going to skip that exercise and we'll just show you what sort does. So there's a command sort. And if let's do cat lengths.txt, and let's do sort lengths.txt. Right, so what did this do? Probably not what we were expecting. So when we did sort on lengths.txt, it basically compared the first character and then sorted kind of lexicographically. So we get 107 total at the top, followed by a blank, followed by this which is not what we wanted. We kind of wanted a numerical sort. So to do a numerical sort, we pass the -n option, and this will tell the sort command to treat the first column of data as numbers and sort based on that. Okay. And again, if we had, instead of 6 files, if this was, you know, 1 million files, we would probably want to redirect the command to another file. So I'll call this sorted lengths.txt. Yeah. And now if we look at the sorted lengths, we have the output of the command that we just ran. Okay. Now, if we wanted I already mentioned the head command, but now we'll see it in practice. So if we do the head command, so we pull the top, the first line off of the file that we pass in, we'll get 9, which is methane. So this was the file that had the smallest number of lines. So if we had basically, you know, 1 million files and we wanted to basically find the file that had the least number of lines, then we've seen some commands on how we might go about doing that. And I'm going to show you how to make that a bit more, even a bit more succinct here in a minute. So we've seen this character here for redirecting output. So like an arrow that redirects output. But when you redirect output, you will also overwrite any output that's in the file if the file already exists. Sometimes you don't want to overwrite the data, you want to actually append data. And that's what this double arrow operator does. So for example, there's a command called, let me clear. There's a command called echo, which prints stuff. So it basically just echoes out whatever you type in. So if we were to echo out hello world into file. Yeah. And then if we were to do cat on the file, then we'll see that that text was basically redirected into the file. If we did echo again and redirected to the file, then we have overwritten the contents of the file. Instead, what we can do is we could do file 2 if we want to append. And now if we do hello world again to file 2, but now we change this to 2 arrows. So now we've appended data. So this double arrow operator appends data to a file rather than overwrites the file. Okay. Now, so we've covered kind of a lot, and with word count, sort, and head, we made it all these intermediate files, and all these intermediate files made it really hard to follow what was actually going on. So let's kind of back up again. So instead of So where was our command? Okay. So we created this sorted lengths intermediate file, which we then passed into this head program. Instead of creating this sorted lengths intermediate file, we can avoid it entirely by, instead of redirecting the output to a file, we can pipe, which is the vertical character or vertical bar, which on my keyboard you can get by hitting Shift, and so above the Enter key there is a forward slash, and if you hit Shift and hit that forward slash key, instead of making a forward slash, Shift and that key makes the pipe character. Your keyboard might be a little bit different depending on where you're joining us from, but that's where you will get the pipe character on my keyboard. So we can pipe the output of that program into the head command directly. And this gives us the same answer. And now actually we can get rid of this sorted lengths, or this lengths.txt intermediate file entirely, and actually just take our word count PDB program and pipe it to the sort program and pipe it to the head program and get the same answer. And so this is the first example of a pipeline, this right here. You've taken these simple Lego bricks, the word count program, the sort program, and the head program, and created a pipeline that will process all of these files, which could be like 1 million files. And this, like here, we're using it to process like the 6 files that match this pattern. But if there were 1 million files that match this pattern, it would run the same command on those 1 million files and return the answer. So this is our first, I think, fairly concrete example of automating what would be a very repetitive kind of task. Okay. So here's a nice little example of that. So we have these like Lego bricks that we're putting together to create this pipeline. So we started out by just running this command, word count, and dumping the output into the terminal, output in the shell. And then we redirect it to a file. And then we use the pipe command to kind of join all these things together. And then now we put the output back in the shell. Of course, we could redirect it to a file as well. Okay.
I have a question. So,
yes.
So can I interchange these commands in the pipeline? So
can you interchange the commands in the pipeline?
Yeah.
So sure. So for example, well, let's see, if we did sort on, what happens if we do the sort on the PDB files? So that, what has that even done? That has sorted the lines of the PDB file by the first column and kind of returned the results all together. So I'm not sure that that's a sensible thing. And now if we were to pipe that to the word count, so the word count program, and count the number of lines, let's see what we get, 107. So basically what this has done is that sorting on a collection of files returns effectively a single file that is sorted according to the ordering of the first column of information by default. And then that whole file was then passed into the word count program, and then the word count program just counted the number of lines. So you can reverse these Lego bricks and kind of put them together however you want, but whether what whether the way in which you assemble them like is giving you the result that you want is a different story. So you kind of have to think about like what is the right order to join these things to get the answer that I'm looking for.
Okay, thank you.
Okay, so what I want to do, I'm just going to have a few more remarks to kind of close this episode, and then because this is such an important topic, I want you guys to have a good probably 5+ minutes to look at some of these exercises. So this is an important idea in the Unix shell kind of philosophy. So we've seen these pipes. So connecting programs like word count and sort together into a stream of input that produces a stream of output. And pretty much all standard Unix tools that will work this way, because this is a part of like the philosophy of the Unix bash shell. And this philosophy of having these different pieces that act like Lego bricks that you can combine together to produce ever more complicated programs has been heavily influential in the data analysis and machine learning community. We will see it when we get to Python and we learn how to do data analysis with pandas. We will see it when we get to machine learning with scikit-learn, and we talk about machine learning pipelines, which compose Lego bricks together to ingest data to build machine learning models and then predict output based on the trained models. When you build these little Lego bricks, it's the same kind of philosophy. We'll see it at the end of the semester when we do image classification with Keras, where we'll create these pipelines both for data processing, but also the neural network itself can be thought of as a pipeline where we're putting together the layers of these neural networks as like little Lego bricks that process the data. So this concept of pipelines has been very influential and continues to be influential. So now we're going to talk a little bit about filters, and then you'll come back and we can look at these exercises. Okay. So basically, well, let me see. So filters. So let me just explain a bit about filters. So you can create these pipelines by connecting these sort of like Lego brick programs together. And then usually what happens is that as the data flows through the pipeline, the amount of data gets smaller and smaller and smaller, because each of these little Lego bricks reduces the data in some way. So for example, our word count program starts with all of these, could be 1 million files. And what does it do? It returns data that summarizes those files by counting the number of lines in each file and produces a much more condensed data set, which then gets passed into the sort program, which acts as a filter that rearranges that data set, although it keeps it at the same size, because it just sorts the number of files. So if there were 1 million files to start with, the word count program would return 1 million lines, where each line had the count of the number of lines in one of the files. The sort would sort that 1 million lines, and then the head program, of course, produces a single line of text. So the volume of data is going smaller and smaller and smaller. And that's also very common. So usually when you create these pipelines, particularly for data analysis, you're creating them in such a way that you start with lots of data and you get progressively smaller amounts of data until maybe at the very far end of the pipeline might be a single number that you're predicting. Okay, so let's go back to our marine biologist pipeline and see some examples. Okay, so we want to move to a different directory. So we want to move to, let's just go up and see. So we need to go into the North Pacific Gyre directory and into this data timestamp directory, and we've got all these files. Okay, so these are kind of like the raw data files. And so we're going to start processing these a little bit. So what if we just use the word count program to get a sense of how big these files are? Okay. And so there's 18 files, so we get something that's 18 files long. But again, if this was millions of files, it might be hard to spot whether there's any anomalies in this data. So let's instead sort numerically, and then let's look at the first 5 lines. I'm going to clear this and rerun that command. Okay, so from here, so now we've sorted them numerically and looked at the first 5 lines. We clearly see that this file has a different number of lines. So that might be a problem. So this is kind of the first step of doing data analysis, kind of making sure that you have good input data. Because if you have corrupted input data and you try to use that for analysis, then the analysis is going to be corrupted and not useful. So in this case, it's like checking like all the files, if they're produced properly from, say, this machine, should be the same size. So the fact that this is too small means that there's somehow an issue with that file. Okay. And again, we can look at the last 5. And then the last 5, we see, okay, well, here's this file here that has a Z at the end of the file name. So some labs have specific naming conventions, and some even scientific instruments have specific naming conventions, so that depending on whether the analysis of the physical specimen went as expected, it might return an exit code that gets into the file name in a certain way, like maybe an A or a B, like in this case. Or if something goes wrong, then I might put a Z, or might put something to indicate that something went wrong analyzing the physical sample. And that's kind of, this is an example of that. So the examples, good examples always enter A or B, so we want to make sure that we exclude this, this file from analysis. So we can find any others. So if we do ls star z.txt, so this will list out any files that match that pattern. So we see that actually there's another file in here that match that pattern too. So there's actually 2 files that we will want to exclude. So how can we do this? Well, there's actually a pattern matching where you can do either like an or pattern matching. So you can use these square brackets and then put characters in between that will say like match any 0 or number of characters, but it must end in either A or B.txt. And so this gives us the files that we actually want to process. So, okay. So now what I want to do is give you guys 5 minutes to look at some of these exercises. So in particular, the one that I will go through together is, well, actually, some of these exercises are new even for me, so I'm going to look at them a little bit. So take 5 minutes and start with this pipe reading comprehension question, and take a look at the rest of the exercises in this episode, and then I'll pick a couple and do them together after 5 minutes. Or if you have one in particular that you'd like to do, if you put it in chat, then we can do that together as well. Set my timer. And I'll be right back. Okay. So let's take a look at some of these exercises. So I'll go through the maybe the first two. So pipe reading comprehension. So there is, we have to go into a different folder. And the data folder. So there's this animal counts, or no, sorry, animals text, right. And this has a date of observation and an animal that was spotted. And we're given a pipeline here, and we want to know basically like what is this final text look like. So the first thing that we're going to do is just kind of walk through these pipeline in stages. So we've catted out the animals.txt file. So that first stage in the pipeline is just going to print out the result of the contents of the file. So if we then do cat.txt and we pipe that to head and 5, well, that's going to take the first 5 lines in the file, 1, 2, 3, 4, and 5. So that's the output there. If we then pipe that into the tail command and look at the last 3 lines, so then that's actually looking at the last 3 lines of the first 5 lines. So that's the last 3 of the first 5, which is, so 1, 2, 3, 4, 5, and then these 3 here. And then we're sorting in reverse order. So what did that do? So it sorted in reverse order based on the results, based on the lines. So that's why you see these are all 3 lines are the same until you get to the day, and you see that it's 5, 6, and 6. And so it reverses the order there. And then it compares the D and the R, and since we're doing reverse sort, R comes after D, and so that's why the first line is rabbit, followed by deer, followed by raccoon. Okay, so that's this kind of building up pipelines one command at a time is a very common way of figuring out what's going on, or of building a pipeline. Okay. So we're going to keep working with this file and this exercise. So we're given this command called cut, which we've never used before. So let's see what it does. So if we cut -d, followed by a comma, followed by F2, oof, lots going on here. So what does this do? So this is the original file. And what we've done is extracted the second column. And if we read through the help menu on the cut command, what we'll find is that the cut command can be used to cut up text files. And this -d is the delimiter. So we have to tell the cut program or the cut command that this file is delimited into columns by commas. And then we want to cut out which fields. So a field is like a column. And so in this case, we want to cut out the second column. So the first column would have been the dates. And the second column was, of course, the animals. So if we change this to a 1, then we get the dates. Oh, that's not what we wanted to do. Okay, let me clear this out. Okay. So that's where that command comes from. So what we want to do is extend the pipeline to find out what animals the file contains. Basically, you want to deduplicate this data and find out what animals are actually in this file. So, and we're given some hints to do this. So we're told that there's this unique command that filters out adjacent matching lines in a file. So if we were to pipe this into the unique command, then nothing has changed because none of these lines, adjacent lines, are matching. So like deer and rabbit don't match, rabbit and raccoon are different. So there's no, so what we need to do is some kind of sorting first. So if we sort, then now we've sorted and we've matched up these adjacent names, or some of them are the same. So they'll get removed, deduplicated when we pass it into unique. And so there's a way to find all of the unique animals in a particular column of data. Now, of course, like this is how you can do these kinds of analysis using bash scripting or using bash commands. We're going to do a lot of analysis of this type in Python using pandas in a couple of weeks' time. Okay, so now I want to move on to the next episode. So actually, well, just to sum up, so we talked about the cat command, head, tail, sort, and word count. So we found some new commands. Cat, head, tail, I use a lot. Sort and word count, not so much. But this concept of pipelines and filters is a really important general idea of how to organize your data analysis that you should try to understand, because we're going to see it again and again and again throughout this semester, or the next few weeks. Okay, loops. So we have about 20 minutes left, and what I want to do is actually skip this episode and talk about shell scripting. And in the shell scripting episode, there is an example of a for loop inside of a shell script. And so I will talk through the concepts of for loops in that context. And then if you really want the nitty-gritty details of for loops, then you can go through this episode on your own. It kind of builds up from the basic ideas of for loops and it processes some data. Okay, shell scripts. So we're going to end with shell scripts, and then I will when I wrap up, I'll mention a couple of very useful places where you can go to learn more about shell scripting and data analysis in Bash. All right, so let's talk about shell scripts. So shell scripts are a great way to reuse commands, to save them and reuse them. So we're going to see how to write shell scripts that run a command or series of commands to process a fixed set of files. We'll see how to run a shell script from the command line, and how to write shell scripts that operate on a set of files where the user provides those files at the command line. So like a shell script that can process different sets of files. Okay, so here we go. So let's clear this out. So we need to be in our molecules file, or directory rather. So we need to go up, down into molecules. Okay, so now we have all of these PDB files and these text files from earlier. So I'm actually just going to remove all the text files to clean this up. Yeah, okay, so I removed all the text files that we created earlier. Okay, so we're going to create our first shell script. And this shell script is by convention going to have a .sh extension. So we're going to use nano to create a shell script called middle.sh. And in this shell script, we're going to write some bash commands like we've been doing. So in this first bash command, we're going to use the head program to look at the first 15 lines of a particular file, octane.pdb. And then we're going to pipe that to the tail command and look at the last 5. So this is kind of going to look at the middle lines of the file, but we're hard coding both the file name and the number of lines to look at in the head command, and also the number of lines to look at in the tail command. Okay. So then we're going to hit Control O to write out the file, and we can hit Enter, and then we can hit Control and X to leave the file. And so now if we look at our shell script, we can see that basically this command is the text that we wrote into that file. Okay, so that's it. So now we are going to run this file as a script. So to do that, we're going to use the program called bash, and bash is a program that reads in text files and processes the contents of the text files as if it was processing bash shell commands like we were writing. And we write middle.sh. So that's it. That's how you execute a bash shell script. So we had a simple shell script, which is just a text file that contains some bash commands. And then we use the bash program and pass that text file in as input. and it ran those commands as if we had typed them ourselves and generated the results. Okay. So let's see how we can make this script a little bit more versatile. So let's go back into the script. So one of the things that would be nice to do is not hard code the name of the file in the script itself. So we might want to allow the user to provide the name of the file. So we can, instead of putting the name of a particular file, we can put $1, which is a special variable that references the first input provided by a user. And it will basically, bash will take that first input and replace the $1 with whatever that input is. So in this case, we'll use this to provide a different file to process each time. Now, because some people might not be as careful to avoid spaces in file names, we will put quotes around this variable, which will, if somebody has a space in their file name, it will make sure that that space is dealt with properly so that this works. So now we're going to hit Control-O and hit Enter and then Control-X. Okay, so now we can look at our script again and see that our script is changed. So we changed the contents. So now what we can do is do bash middle, and if we pass in the name of the file that was in there before, Octane, we get the same results, yep, which is what we would expect. But now we can pass in another file like Cubane, and the same script will now be applied to Cubane. And we can do another one, methane, and get yet more information.
Excuse me?
Yes.
Sorry, so basically bash reads the $sign with the 1 as an input?
Yes. So
or
that's
just the $sign?
The $1 is a special variable that you can use in your bash scripts so that the $1 will be replaced by the first input provided by the user at the command line. So every time we run this script with a different input, that when the script is run, the $1 is taking a different value.
Yes, clear, thank you.
Mm-hmm. Okay. So how else could we make this script maybe a little bit more general? So let's look at it again. So we're hard coding these numbers 15 and 5. So we could change those. We could make this $2 and this $3, put quotes around it. And then we'll write out, enter. Okay, so now we can change the behavior of the program even more. So instead of, well, let's go up and kind of do the last 5 of the first 15 lines. So this is going to give us the same output as we got up here, the very first version of the script. But now we can change this to say, let's take the first 20 lines and the last 8. And so now we get different data. So what we've done here is kind of a simple example where we're reusing a pipeline that we've constructed inside a bash script, and we're generalizing it by making it so that you can run the same pipeline on different inputs of data using these special $1, $2, $3, and so forth arguments. Okay. Now, once you get bash scripts that are, even relatively, well, any bash script you write, you should put a little comment at the top that lets you know what this bash script does. So this one selects lines from the middle of a file And then, you might want to give a usage example. So the usage would be bash middle.sh followed by the file name, followed by, the end line and the number of lines, something like this. So it's basically like just a little bit of documentation to kind of let you know what the script is doing. And then we will save it. And now look at the file again. And so you can see now, it's saved the contents of our file. Okay. All right, so let's look at another example. So remember our pipeline where we were sorting files. So we had this this word count program, and we passed in the PDB files, and then we sorted them numerically. Yeah. So let's suppose that this was a pipeline that we wanted to reuse over and over. So we could create actually a bash script. We could echo this command, which instead of executing the command, actually I don't want to do that, because when you echo it, it dumps out all of it substitutes for the star.pdb. So instead what we'll do is we will just do it this way. So nano sorted.sh. And so now let's put the word count program in here. So we'll do word count star.pdb sort in. And then we'll do Control O, enter, Control X. Okay, so now if we do bash and sorted, we get the same results. Great. So let's edit this again. So we are going to sort files by their length in lines.
Excuse me, can I ask you a question?
Yep.
How did the basically you didn't enter anything like in star? How did it know that you are executing the files that are in? You didn't put a $sign.
Right. So here, all that's happening when I don't have a $sign. Let me just finish writing. I'll put this file 1, file 2. Okay. Right. So when I run this script, and I still have star.pdb. So when I run the script using this command, it just executes. Bash basically ignores these comments and then just runs this command at the command line as if I had typed it. So here, that's why when it runs this command, it fills in all of the PDB files here.
In the same directory, right?
I'm sorry?
In the same directory.
In the same directory, exactly, in the same directory. If we try to run this in a different directory, it would just fail. In fact, if we wanted to do that, I'll just show you. So if I was to copy this sorted script to the parent directory, and the parent directory has no PDB files in it, right? So then if I went into the parent directory, oops, I went back to my home directory. So if I go back to that parent directory, so here's that sorted script. If I was to bash this sorted script, it fails because there's no, when it tries to do a pattern match on this .pdb, there's nothing in this directory that matches that pattern, so it just fails. So let's get back to where we were. Okay, so now if we do bash sorted, okay. So now we're going to generalize this. So because we don't want that to be the case, so it really shouldn't be the case that this script will only work if we happen to run it in the right directory. So what we can do is we can, instead of this, we can replace it not with $1, which would only allow us to pass in a single file. What we want to be able to do is pass in potentially a whole bunch of files. And we might want to be able to use pattern matching to determine the files that actually get passed in. So here we can use a special variable called $at. And so this is here in the notes. So with $at, now we can use the script like this. Bash sorted star.pdb. So now this script will count the lines in any one or more files that we pass in. And because of the bash is like small pieces loosely joined philosophy, we can use pattern matching to actually determine the files that we would pass in. So for example, if we were to try this by passing in, so let's see where are some other files that we could look at. In the data directory, oops. In the data directory, okay, so there's some text files here. So if I list star.txt, so here's some text files. Now what I could do is I could use this bash script to pass in a collection of files. And these files aren't even in this directory. They're in a completely different directory. But I can pass in the file paths, and then the word count command will go and count those files. So this script is now much more reusable. And I could even use it on multiple examples. So I could do, I could even do something like this, PDB. So I'll count all of the PDB files. I'll count all of the text files in this directory that I looked at before. And in the other, there's a creatures directory that has even more data in there. Dat. And it will just handle it, because what bash will do is it expands these wildcard pattern matches out to a long list. And you can actually see that using the echo command. If we did echo, actually, if I was to delete this, so what actually happens is bash replaces this with this, and then passes all of these files into this. And this is super handy, because here, this is like, I don't know, a dozen files, which it would be annoying to write out, but not impossible. But if you had 1 million files that you wanted to process, then you could come up with some pattern matching to extract those 1 million files that could be spread all over the file system and pass them into this bash script and then get your results. Okay, so I didn't quite finish. I gave you a flavor of bash scripting. I want to use the last 5 minutes to kind of wrap up and talk about places you can go to learn more information about bash scripting, and then give you some opportunity for questions. But the rest of this episode kind of gives you ever more kind of complicated examples of bash scripts, including a bash script to kind of process Nell's data analysis pipeline, which uses for loops. And you can see that what happens is that you use this $at special variable to pass in the list of files that are going to be processed in your loop. And this pattern is very, very common. And many of our users at on IBEX and Shaheen and the people I work with doing not only data analysis and machine learning, but bioinformatics and genomics and geosciences have workflows that fit into this kind of pattern where they have a big collection of files that need to be processed. They need to do the same kind of stuff on each file, and they use bash scripting and for loops and whatnot to do that in an automated fashion. Okay, so does anyone have any questions for me about what we covered today? And then I will point out some resources where you can learn some more information about this topic.
Thank you very much for the clear workshop. I would like to ask if there's an advantage of using bash scripting over Python script or JavaScript.
So that's a great question. So one of the things that, okay, so bash scripting, when I use bash in my own work, it's typically not to directly do the data analysis itself, but rather to help glue together different pieces of the data analysis pipeline. So for example, it might be that you're doing most of your data analysis using Python scripts. But you need to run those Python scripts on different input data, and you need to do this, many times, maybe, and have those results or have those computations be spread over a cluster or use many cores on the same machine. So bash would be a way to do that. So you could use a bash script that, instead of calling like a word count program, actually calls a Python script and passes data files into the Python script. The Python script is doing all of your work, but you're using bash to collect the data files for analysis and then pass them directly into the Python script itself. Another example would be in bioinformatics and genomics data processing pipelines, you often have command line programs that might be written in C. You might have other tools that have been written in Java. I've seen pipelines that use tools that are written in 3 to 6 different programming languages. So you use bash to glue together a workflow that allows you to process different stages of the workflow using these different tools, but combine it all together using pipes or for loops. So you can glue together all these different tools, which might be written in different languages, using the common kind of language of bash. So hopefully that gives you some flavor of how, in addition to the need to use bash to interact with the file system and interact with remote computing systems and things like that.
Okay, thank you very much. That's very clear.
Okay. Any other questions?
I have a question, but probably it's weird. But so when you do bash computations, so can I run them in parallel too, or they run in serial? So
right. So many bash tools are parallelized, not all of them, but some of them are already parallelized and will just kind of handle using as many cores as are available on your machine. There are, and I'll mention this in a minute for more kind of advanced use cases, there is because if you think about the process of creating these pipelines, so many of the pipelines that we created, obviously the pipeline itself is kind of a serial entity where you've got each step comes before the ones that follow it, right? But if you think about that, like, it's a data parallel process. So each input file needs to go through that pipeline. but actually all the input files could go through the pipeline at the same time. And then the results kind of join together at the end because there's no intermediate dependencies. Like if you're just counting, like in these programs, we were counting the number of lines in a file. Well, if I could, run each of the files on its own core or its own thread, then I could just do that whole pipeline in parallel and then knit the results together at the end. So there's a tool called, I think it's GNU Parallel or something like that, that is in a book that I'm about to show you in a minute, that will parallelize those kinds of bash pipelines. The trivial or data parallel pipelines, it will just parallelize for you with a single command.
Okay, thank you.
You're welcome. Any other questions? Okay, in that case, I will end by showing you a few sources of where to go for more information. So the first thing that I would do is go ahead and finish the material that we weren't able to cover today. So that would be the loops episode and then the finding things episode. So go ahead and take a look at those, particularly the loops, because that will help you get a sense of how for loops work in Bash, which will help you if you've not seen for loops before. We're going to see for loops again in Python in a couple of weeks. And again in the machine learning with scikit-learn, and again in, well, maybe again with image classification, Keras, or maybe not. But definitely in Python and definitely in machine learning with scikit-learn, we'll talk about for loops. When you're done with that, there's actually a second set of software carpentry lessons called Shell Extras. And the link to that is here in the, on the lesson kind of syllabus. And I'll put this below the YouTube file or the YouTube video in the extra details section. But there's some extra Shell material, which talks about some more advanced topics, how to work remotely. So if you want to know more about how to log in, either if you're here at KAUST, you want to know how to log into IBEX or Shaheen, or how probably your own university or company, if they have cluster computing resources on premise, how you could log in remotely, or if you're going to use the cloud, the public cloud like Google or Amazon or Microsoft Azure, and you want to log into some cloud resources, it would be the same principles. How to move data back and forth, permissions, more about directory structure, shell variables. So these things are shell variables are useful for writing more advanced bash scripts. So more advanced topics that are kind of beyond the core, the fundamentals that I wanted to talk about today. The next thing that I wanted to do is give a plug for a very cool little book, the second edition of which I think is almost finished. But this is a book about how to do data science at the command line. It talks about how to build on the principles that I've kind of taught you today, and how to use, instead of simple programs like word count, sort, unique, things like this, how to use other command line tools that might require more work to install, like they're not necessarily included by default in like Mac or Linux, and definitely not on Windows. But it talks to you how to install these tools and how you can use these tools to do very sophisticated data analysis entirely from the command line. And it's a really interesting and different take on data analysis. There's lots of books on data analysis in Python. There's lots of books on data analysis in R, or JavaScript, or what have you. And those books are all great and they all have their place. But there's some really interesting ideas about how you can do quite a lot of advanced data analysis very efficiently with just these command line tools. So I want to make a plug for this book because I think it's really cool, and I know that there's a new edition that's on its way. Okay, so those are the two resources that I would kind of focus on. And let me put these links, stop sharing for a minute. I'm going to put these links. And so link to the book I recommended. And then the link to the extra shell material. And again, these will be on the YouTube channel, which I can grab. I'll just grab that link too while I have it. And I will probably put this up, today's class up either this evening or maybe tomorrow morning, definitely tomorrow at the latest. So, so here's the link to the YouTube channel. You know, please subscribe and all of that if you want to be notified when we've got new content out. We're really keen to kind of get our training and our knowledge to take advantage of the difficulties that we're all in because of this pandemic, and get a lot of the knowledge that would normally only be available to KAUST students and faculty, and kind of make it more widely available to increase its impact, because we do have a lot of really good training here at KAUST and a lot of really knowledgeable scientists, some of whom you'll meet on this course later in these workshops. And we're trying to really get this material out so more people can benefit from it. So I don't have anything else. Thank you for spending the afternoon with me, and I hope you found it useful and informative. And next week, we will be talking about an introduction to managing your software stacks using Conda and pip. So this is kind of a prerequisite for, or I think of it as a prerequisite for learning Python, because there's so much Python-based software that before you can really get started learning it, it's worthwhile taking the time to learn how to install it and manage it, so that you can use the greatest and latest libraries that are available for the problem that you have. So we're going to talk about that next week. And then the following week, we'll be getting into Python proper. So hopefully you will have registered for the courses for next week. And then if so, I'll see you next week.
Thank you.
You're most welcome. Thank you for coming.
Thank you.
Thank you.
You're welcome. All right, bye guys.